Good morning, everyone. So as you know, this week will be entirely revision. I'm going to go through the sample paper, and I'm going to do it in a way that I'll answer all the questions exactly the way you'd be expected to answer them in the final exam. I'm not going to skip anything or go over anything. What I write down is what you would write down for the answer. Before I get onto that, just a couple of announcements in case you haven't noticed or checked your student email or the announcements page, which again, you're supposed to. But in case you haven't, there's still the Quiz 5 prep workshop today on this campus in Building G, run by Mesh, so you can still register for that now if you want to. Head over there. It gives you a bit of a break between the lecture and the workshop. So Quiz 5 is just now released, and it covers the content in weeks. Well, it covers simple linear regression and correlation. So all that stuff we did about looking at scatter plots, what do you think the correlation coefficient is, looking at output for simple linear regression. Here's the slope estimate, here's the intercept estimate, here's the standard error, all that kind of stuff. So it'll be based on all that kind of stuff from those weeks where we discuss simple linear regression and correlation. The next thing is that Mesh will also be running a final exam prep workshop. So they're doing a dedicated biometry workshop here at Hawkesbury, and that is on November 5th from 9 to 11. So register for that one if you want to go. Mesh will have a sample paper. It's another sample paper that is different from the one that I'm going to show you, and they do a really excellent job of creating sample papers that are very similar to what the real thing is going to be. Well, again, don't assume that they're going to be exactly the same or anything like that. Similar level of difficulty kind of thing. Obviously, similar structure, similar topics, all that kind of stuff. So you get two exam papers to look at, the one we look at today and the one that you will look at if you go to the Mesh workshop. If you can't make that one at Hawkesbury on Monday, there is another thing happening in Parramatta in 2 successive weeks. So on the Monday as well in Parramatta, and then the next following Monday after that, Mesh is trialing a new concept called Maths Cafe, where it'll be basically a workshop for a whole bunch of math subjects, all the subjects that are supported by Mesh. So there'll be students from other subjects there, like quantitative thinking or Maths 1A or whatever. And the idea is that you don't need to register, you just turn up. It's a very informal atmosphere. It runs for 4 hours in total. There'll be a lot of Mesh staff on hand. Someone will give you a sample paper. You can have a crack at it. They'll help you out when you need help. It's just designed to be less of a structured, formal atmosphere. They've got, actually there's a flyer here. You can actually see in the flyer right at the top left, there's a little chi-squared formula. Very relevant for us. So there's going to be food, coffee, tea, all that kind of stuff. It's a new idea. You don't need to register, but it is on Parramatta South Campus. So you're welcome to turn up to either or both. Doesn't matter if you want to go to the Hawkesbury dedicated one or if Parramatta is more convenient for you. That's all good. Okay, so another thing I wanted to say before I get started, with regards to your revision, I may have informally mentioned this to a few people so far, but the content we covered in week 12 won't be assessed in the final exam, and obviously not in Quiz 5 because that's, as I said, only simple linear regression and correlation. So week 12 was all that stuff about non-normal distributions, binomial, Poisson, and the transformations. So again, it's a university subject. You're expected to learn it. You're expected to know these techniques, but I will tell you to take some of the pressure off that kind of stuff won't be assessed. So if you struggled with that week, don't worry about it. So I put a note there in learning materials, and I also added a note to the actual week as well, so that if anyone goes to click on it when they're studying, they can see that that content won't be assessed at any point. Okay, so what I will do is work through the sample paper, but I did say that first I would take any requests. If you had anything specific you wanted me to go over, does anyone have any? I will probably, to be fair, we'll cover a lot of ground through the sample paper, but if you've got anything specific you want me to do, let me know. Has anyone got any particular questions? That's fine. So I will work through the paper. As I said, I'm going to write down the answers exactly as you would write them down in the real paper. I'm not going to ask for a lot. I'm not going to be trying to engage you that much this lecture because we did that last week with regards to revision. I'm just going to dial in. Here's how you do it. You can watch the recording later if you feel like I went too fast or something like that. You've got 3 recordings for this week all covering the same thing. So first off, the structure of the paper. It's 2 hours, obviously. If you check the learning guide, it is open book. And there's no restrictions on that. So just like it was for the computer skills test, let me just double check the phrasing. There you go. Final examination is open book. And there are no restrictions on what you can take in. So if you want, you can take in the textbook, the Mind on Statistics textbook. You take in any of your written notes, single-sided, double-sided. There's no limit on the quantity or the number or what kind of things you can and can't have. Obviously, the only restrictions are the standard ones with regards to electronic devices. A scientific calculator is allowed, nothing else. No phones, no laptops, anything that isn't, the definition is anything that doesn't primarily function as a calculator is not allowed into the final exam. So aside from that, 2 hours and open book. Let's get started. So the structure will be very similar to this paper that I'm going to go through in the sense that it'll be roughly in the order of the topics as we've done them throughout the semester. So the first question in the paper is very basic stuff. Means, medians, quartiles, box plots, all that kind of very simple statistics that we discussed before we ever got into hypothesis testing. So there's some easy marks to get here as long as you are paying attention. So they give you a box plot. It displays a sample of 25 observations, and they ask us to estimate the following things. So first up, the median, as always in a box plot, that is the thick black line in the center of the plot. You don't have to do this, preferable to take a ruler in for things like this, or if you want to draw a picture or some kind of plot, which is not necessarily required, but may help you, as I would suggest, draw a picture. It'll help you understand what's happening. So if I look at that thick black line and follow it down to the corresponding spot along the horizontal axis, I need to estimate that value. And looking at it, it's not halfway, it's a bit less than halfway. So I'd probably say around about 42 is approximately what I think that value would be. So that's all it is. Median is equal to 42. That's all you need to answer the question in the final. Okay? Very easy mark. There's some leeway there, obviously. That may not be exactly 42. If you don't get it very obviously wrong, if you said 41 or 43 or something like that, that obviously cannot be the case. But no one's going to be nitpicking about if it was 41.8 and you said 42 kind of thing. Okay? Clearly, and that's where probably marking the exam paper or drawing another plot in your workbook might help to indicate that you understand what a median is. You followed that line down to where it hit the x-axis. That's the number you thought it was going to be. So the next one, and by the way, feel free to stop me at any point if I say something that doesn't make sense. As I said, I'm just going to kind of mow through. So stop me if something doesn't make sense. The next one they want is the lower quartile. So the quartiles are given by the upper and lower bounds of the box plot. The low edge of the box plot tells us where the first quartile is, the number in the sample data that has 25% of all values below it and 75% of all values above it, approximately. So again, I do the same thing. I follow that down to the x-axis using my ruler, and I can see it's somewhere probably between 40 and 41, I would say. And again, no one's gonna savage you if you get it wrong. You could probably say 40 and you'd be fine. I might say 40.5. But again, it's very clear to the examiner that I know what I'm doing. I've clearly identified where the lower quartile should be and followed it down to the x-axis. Okay. Next one, upper quartile, exactly the same thing. Follow it down the upper edge of the box. We call that the upper quartile. That is the number that has now 75% of all values below it and 25% of all values above it. That's why it's called a quartile. They all split the set into equal quarters. And if I follow that down, again, it looks very close to 45. You'd probably be within your rights to say 45 or 44.5 or something like that. It's very, very close, so I'm just going to say 45. Okay? Easy marks to get. Easy marks to get as long as you don't make a very simple mistake. So pretty gentle introduction so far. How many points are more than 1.5 times the interquartile range from the box? That's very easy because the way we always draw box plots by convention is that we will label or identify individually any points that fall out of the 1.5 times interquartile range as outliers. Software will do that for you automatically. You would do it if you drew one yourself. There's only 2 points. 2 points that fall outside that range. And again, that's all you need to write, okay? No maths really yet. All we've done is look at a picture. Very easy going start, okay? So a couple of things, just, as I said, the first question will be similar difficulty, similar range of topics. It's going to cover the very first stuff we did in the semester. So it'll be stuff like this. Quartiles, numerical summaries like the mean and the median and all that kind of stuff. So maybe to take note of a couple of important points, if someone asks you to interpret or maybe give a value for the spread of a box plot, one good value for spread, the range is a value of spread. You could just take the minimum number minus the maximum number. That gives you a measure of spread, but it's not a very good one because it's very sensitive to outliers. The better measure for spread, if we're looking at a box plot, is the interquartile range, the distance between the lower and upper quartiles, which were 45 and 40.5 roughly. Okay? In which case, my measure of spread would be IQR. We call that the interquartile range. Interquartile range. That gives us a decent measure of spread. It gives us the middle 50% of the data. And it is given by the difference between those two values. 45 minus 40.5. So we'd say the interquartile range is about 4.5. Okay? Outliers are always outside of the 1.5 times that range. So if I said 4.5 is my interquartile range, I take 1.5 times that amount. Visually, you go 1 plus a half, looks like it's about there. That should be the maximum length that the whiskers can possibly be. Okay? The whiskers will only be drawn to the last point in the sample data that lies inside of that range. So you can see I probably overestimated the value because they've regarded that as outliers there. It's probably a bit shorter than the way I've pictured it. But that's the idea. 1.5 times the interquartile range. That should give you your maximum distance for your whiskers on the box plot. Anything outside of that is an outlier. And that interquartile range is your measure of spread. Okay? So there we go. First part of the first question done. Oh, the other thing you can look at, I left a little note for me there on the side, is the skew. The shape of the distribution. So you had a similar question in the computer skills test, which was a little bit tricky, and most people got it wrong, I think, that asks you if a particular box plot was left or right skewed. You're looking for where most of the points are spread out into a bigger range. Are they more spread out towards the upper end or towards the lower end? And you can't necessarily always tell that just by the outliers and the whiskers. Probably your best bet, if you have the information available, is to check if the mean is bigger or smaller than the median. That'll tell you which way it's skewed. But again, you're just roughly looking for which direction most of the numbers are spread out. Looking at this, I can see that that median line is pushed more up towards the lower end of the box. That probably indicates to me that it's more spread out towards the upper side. And if you're more spread out in that direction, I'd say you were right skewed, spread out towards the right. Okay? So just some ideas about spread and shape and that kind of stuff when we look at box plots. Okay, any questions so far? As I said, that's all you have to write. The final exam, 4 questions, 4 subparts of a question done. Very, very simple. All right, so the following are a sample of 13 observations arranged in order. That's good that they've arranged it in order because the first question they ask us is to find the median. And before you find the median, you must make sure that the numbers are arranged in ascending order. Otherwise, you're just going to get nonsense. A very common mistake when people are in exam pressure, they just look at a list of numbers and find the one in the middle without actually arranging it first, and it's not going to give you the correct answer. So I have 13 observations. That's an odd number. That means the median should be the 13 plus 1 divided by 2 value. 13 plus 1 is 14, divided by 2. That gives me the 7th number. So I count in my list 1, 2, 3, 4, 5, 6, 7. Just to double check, if I count the same distance from the top, 1, 2, 3, 4, 5, 6, 7, I land on the same value. That is the number that splits the set in half. That is your median value, 20.1. Okay. Which of the following is most likely the mean? So the mean is very different. Obviously, it's an average number. You need to look at that list of numbers, and usually there's going to be some very obvious incorrect candidates. For instance, I would immediately eliminate 8.8. That stuck out like a sore thumb to me. The smallest value in the set is 8.8. The mean cannot be equal to the smallest value. That's mathematically impossible. Cannot be down there. I'm expecting the mean to be pretty close to the median, okay? Unless the set is very skewed, right or left skewed. I'm expecting the number to be somewhere around the 20 mark, okay? Looking at 29.9, that as well is the maximum. The mean can't be the maximum and it can't be the minimum. So we've got three options left. 16.6, if I look at where that is located, that's down here. Probably not. It looks like the set is evenly spread, too evenly spread for the mean to be that far away from the median. Similarly for 23, that's up here. I'm probably guessing that the correct answer is 20.34. That's the only one that it could possibly be, I think. Okay, that's the one that's closest to the median. And typically the mean will be pretty close to the median as long as the set isn't heavily skewed in any way. Okay, remember the normal distribution, the classic example. Its mean is equal to its median by definition. That's not true of all sets, definitely, especially heavily skewed ones, but you expect it to be pretty close to that value. Okay, so there we go. We've answered those two subparts of the question. All right. So the next one says, a species of frog has a mean weight of 32 grams and a standard deviation of 3 grams. To one decimal place, what proportion of the population must be contained in the range 23 to 41 grams? Now, there's a couple of things I think of whenever anyone says what proportion is contained in this range. Most of what we've done in, from weeks 5 to 7 or 8 was those kinds of questions, but in the context of normal distributions. And you'd say, here's a normal distribution, what proportion is between these two values? However, they said nothing there about that being a normal distribution. I have no reason to assume it's a normal distribution. And also, I don't have a computer with me to work out the p-values. So that should immediately eliminate that possibility. The other thing that we can use to work out proportions like that is something called, if you don't remember, Chebyshev's theorem. Chebyshev's theorem. And Chebyshev's theorem states that we will have at least a proportion of 1 minus 1 on k squared of the population, any population, doesn't matter how it's distributed, at least 1 minus 1 on k squared, I should say a proportion, to make it clear that it's a proportion. Proportion of the population within the range of the mean plus or minus that multiple of the standard deviation. Okay, and that's quite a tricky theorem to remember. It's just a prescription. It tells you if you have a plus or minus 1 standard deviation range, or 2 standard deviation range, or 3 standard deviation range, plus or minus that either side of the mean should contain at least that proportion, 1 over a half, 1 on 2 squared, 1 on 3 squared, 1 on 4 squared, whatever your number of standard deviations is. Okay? So we need to say, what have we got here? Well, in our particular question, we have that the mean was 32 grams. And we need to know how many standard deviations we are from the mean. So the standard deviation is 3 grams. So 23 and 41, how many standard deviations are they from the mean? That's what I want to work out. You can do this in your head if you're good. 23 minus 32, that's a difference of 9. 9 divided by the standard deviation of 3 tells me that 23 is 3 standard deviations below the mean, and similarly 41 is 3 standard deviations above the mean. If that's too fast for you, then break it down and go slowly. I need to know how far away are these guys from this guy in terms of multiples of the standard deviation, 1, 2, 3, 4. And this is a z-score. which we use mostly when we're talking about normal distributions, but you can use it in anything. It just tells you the number of standard deviations you are from the mean. So I'll work out how many standard deviations the number 23 is from the mean by calculating the difference between that number and the mean, which was 32. Put in the grams there, and dividing it by the standard deviation. And that gives me -9 over 3, -3. And my units cancel, for anyone who's pedantic about that like I am. So I know that 23 is 3 standard deviations below the mean. How many standard deviations is 41 from the mean? So I go 41 minus the mean divided by the standard deviation, and I get +9 over 3. It's +3. So it is 3 standard deviations above the mean. So now I know what I'm looking at. The range that I'm looking at is the mean plus or minus 3 standard deviations. So we have k equals 3 in Chebyshev's theorem. In Chebyshev's theorem. Therefore, we have 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 8/9 proportion of frogs. Again, I'm being specific to the question, weigh between those values, 23 grams and 41 grams. I need to read the question carefully, though. It did say, I'm almost done, but it did say to 1 decimal place. So I've only given it as a fraction. So I could do it as a proportion, 8 divided by 9 to 1 decimal place. If you plug that into your calculator, 8 divided by 9 is 0.8888. So it's 0.9 proportion. Or if I express it as a percentage to 1 decimal place, it's 88.9%. Okay, you can plug 8/9 into your calculator to check that. So I put the stuff in blue, what I would write for the question to answer it in the exam. In red, I just put that up there to remind you of what the theorem was, Chebyshev's theorem. You don't need to rewrite that into the exam. Only the stuff in blue is what I would write. And even some of that isn't required. If you're good and you know what you're doing and you think you're not going to make a mistake, you can work out those z-scores in your head and just say 23 grams is 3 standard deviations below the mean, 41 is 3 standard deviations above the mean, and then go from there. You don't have to work it out explicitly the way I did. But I find in an exam situation when you're nervous and you're amped up, it's easy to make simple mistakes, so it's a good idea to try and slow down and write it all out cleanly and neatly. Okay? So that question was an application of Chebyshev's theorem. If I'm within 3 standard deviations of the mean, I should contain at least. I should clarify that. It's only at least. Could definitely be more. Could definitely be more, but at least that proportion of frogs. About 88% of all frogs weigh between those two values, 23 and 41 grams. Okay? Any questions? So that was the first proper question, I guess, that a question where you had to actually use your brain and do some maths. The others were all fairly basic and required a little bit of working. So the stuff in blue is what I would include as my answer. Okay? All right. Hypertension is commonly defined as a systolic blood pressure above 144 milligrams of mercury. If a physician is given a report stating that a sample of 4 women has an average systolic blood pressure below 140 millimeters of mercury, can the physician conclude that none of the women has hypertension? The answer is no. The idea that they're trying to get across is that just because the mean value is within the correct range, it doesn't mean that all the sample values are within the correct range. So for instance, I could have 3 women who had a systolic blood pressure below the mean. Let's say 3 women who had systolic blood pressure of 130 millimeters of mercury, okay? And 1 person who was over, 1 person who was like 141 millimeters of mercury. Add them all together and divide by 4 to get your average. The average will be a number in the correct range. It'll be below 140 millimeters of mercury. But it's not true to say that all the women, therefore, had the correct blood pressure, is it? because there's a counterexample. Just one counterexample, that's all you need to prove it wrong. You don't need to prove it wrong in general. If someone gives you a general statement in maths, all you need is a single specific example to say that that is wrong. It doesn't apply everywhere. And there you go. Okay? You could even flip it around. You could have 3 women whose blood pressure was above 140 millimeters of mercury, and one who was just so far below it that it skewed the mean down into that range. Okay? So the answer is no. Equals, I'm just going to say, instead of bothering to work it out in my calculator, I'm just going to say that the mean is less than 140. It definitely will be. As an example, or counterexample, consider this, and then I would say, therefore, it is possible to get a mean systolic blood pressure below 140 millimeters of mercury when some women, when not all women have a systolic blood pressure in that range. Below 140. The wording is up to you. Again, try and be specific to the question. I'm clearly answering no. The physician cannot include that none of the women has hypertension. And here's a particular counterexample. One woman technically has hypertension, but the average was still below that range. Okay? So they cannot conclude, simply because the average is below that value, that all 4 of them must be below that value. Okay? That's not the way means work. Any questions? All good? I know I can see some of you writing down. I don't want to pause for too long. As I said, you can check the recording later if you want to double back. I'll try and stay on it for as long as I can, but I want to make sure that we get through as much of this as we can. Okay, so question 2 says, it's about probability now. So question 1, again, was all basic, you'll notice. Means, medians, and Chebyshev's theorem was a little bit from left field, but we did do that in the earlier weeks of the semester. So now we're moving on to one of the next big topics we did in this semester, which was probability. And that was what we had to discuss before we moved on to the big stuff about normal distributions and hypothesis tests and all that kind of stuff, which is related. So, I should have gotten rid of that. They tell me that I have 4 events, A, B, C, and D. Whatever they are, it doesn't matter. They tell me that the events A and B are disjoint. And they tell me that the events C and D are independent. And then they give me some known probabilities for these events. The probability of A occurring, B, C, and D. Okay? And they ask me to calculate, based on that information, that A and B are disjoint, C and D are independent, and that these are their individual probabilities. They ask me to calculate the following 4 things. Again, read the question carefully, just like in your online quizzes. Make sure you quote it to the correct number of decimal places. So I want to calculate the probability of not A. So the probability of A occurring is about 53%, according to what they've told me. Therefore, the probability of A not occurring is 1 minus that value, 0.47. Simple as that. These things are complementary. If I tell you that the probability of it raining today is 25%, then the probability of it not raining must be 75%. Okay? They add up to be 100%. They're complementary. They can't both happen at the same time. Something can't happen and not happen, right? So those 2 events can't overlap. And they are specifically complementary. They add up to be 1 as a probability or 100% as a percentage. Okay? So they gave me A. I can work out not A based on subtracting it from 1. All good? The next one, P of A or B. So this symbol here, I'll just rewrite it for you. It means A or B. What's the probability of either of these events occurring? It could be only A or only B or both of them. That's what it accounts for when you say A or B. So to calculate that probability, the formula is that I take the probability of A and add it to the probability of B and subtract the probability of both events occurring. Okay. If you remember from the lectures we talked about Venn diagrams, there's an overlap. If there's an overlap between two events where they both can occur, you need to subtract the probability of that happening from your calculation. Otherwise, you'll double count it. I add up A and I add up B, and I've double counted the bit in the middle where they overlap it when I counted both A and B independently. So I need to subtract one of those overlaps from the thing, which is what I've done there. However, that overlap is equal to 0. That is equal to 0. I know that because they told me that A and B are disjoint, and that is by definition what it means. That A and B are disjoint means that they can't both occur at the same time. P of A and B is equal to 0. So now calculating the probability of A or B occurring is very simple. I just need to add those two numbers together. I've got P of A. They told me that. They told me it's 0.53. And they told me that P of B is 0.19. So I just add those numbers together, and I get 0.72. Okay? Happy with that? So the next one says the probability of C and D occurring. So that's what that symbol means, the upside down horseshoe. The other one is A or B. This one is AND. The other one's OR. This one is AND. So both of them happening at the same time. Now, there's only one way I can work this out, given what they've told me, and that is as the product of the probability of both of those occurring individually. The only reason I can write that combined probability in that way is because the events are independent. The probability of one thing happening does not affect the probability of another thing happening. That's what it means to be independent. The classic example, flipping a coin. If I flip a coin 10 times in a row and get 10 heads, the probability of getting heads on the 11th flip is 50%. It's still 50%. Regardless of however many coins I've flipped previously, it is still 50%. The probability is completely independent of all those other events. So if you have independent events, you can calculate them simply as the product of their individual probabilities, which they've told us P of C was 0.25 and P of D was 0.8. So you should get 0.2. And I have to be careful to 2 decimal places. Even if your calculator comes out to give you exactly 0.2, pay attention to the way the question was worded. It did say to quote it to 2 decimal places, so you should just tack on a 0 there. So now it's been given to 2 decimal places. Okay. Any questions about that? The last one, P of C or D. So this is the horseshoe symbol again, which we know means or. Probability of getting a P of C or D is equal to, again, we need that formula. The formula that I used for part 2, it's still the same formula, but now we're just talking about it for C and D. So I take the probability that C occurs, the probability that D occurs, and I need to subtract one of them for when it both occurs. Okay. And I can work this out now because I have all of these numbers. They gave me P of C, they gave me P of D, and we just worked out the joint probability. We worked out the probability of C and D both occurring was 0.2. So the rest is just substitution. C, probability that that occurs is 25%. Probability that D occurs is 80%. Subtract the probability that they both occur is 20%, and that comes out to be 85%, or 0.85 as a proportion. And again, this is something you want to check when you go back through your paper, that you've covered all these little details, the rounding, in this case all to 2 decimal places. Okay, so some basic probability questions. That's, I think, the degree of difficulty you should expect. If you spend half a page working out one of these answers, you're not doing it right. Move on to something else and don't waste any more time on it. That's my advice. And that's probably the general rule for almost all of the questions in the exam. You're going to see that none of them actually require that much working. I mean, we're up to question 2 now. The most working we've done was probably for the Chebyshev's theorem one, and even that, some of the working was optional. I was just trying to make it very clear as to what I was doing and how I was calculating it for you. So if you're spending more than like half a page on something, maybe move on to something else and come back to it later, because nothing should take that long. There are a couple of questions that I'll point out when we get to them that might take a little bit of time. But as a general rule, these kind of things should be short and sharp. Okay? Any questions about the probability side of things? Cool. So the next one is a normal probability plot. We've seen a few of them over the last few weeks. Some of them in the context of just checking for whether the data is normally distributed. We did that a while ago. And then we did some weird Frankenstein combination of variables when we looked at studentized residuals and whether or not they were normally distributed. That let us test one of the assumptions of simple linear regression. Let us test if all the variables were roughly normally distributed around the line. So all it is you're looking for all of the points to lie within that red dashed confidence envelope. If they all lie inside that envelope, you can say that you have something that is normally distributed. If they don't, your very first thing is to say that it says describe the distribution of the data. My description would be that the data is not normally distributed. That's the very first obvious thing that jumps out at me. Not normally distributed. But I should be a little bit more specific because that covers a fair few things. Can I tell if it's left skewed or right skewed or anything like that? This is one of those shapes that wasn't either left skewed or right skewed. But you can see over here, these numbers down the lower end of the data, they've been arranged in ascending order. They are smaller than I would expect them to be from a normal distribution. Expect to see from something that's normally distributed. And so you say something along those lines. The smaller values are smaller. I know that sounds strange. The smaller values are smaller and the larger values are larger than we would expect. Are larger than we would expect from a normal distribution. So you've clearly identified that you know it's not normally distributed simply by virtue of the fact that all of the points are not inside that confidence envelope. Secondly, just be a little bit more specific to the shape as to what you see happen. Why isn't it normally distributed? What do you see going on, if anything? Is there some kind of pattern to the way that data is playing out? Okay. So that's all we need for that question. Yeah.
Say you don't one without those LIs that you marked.
Mm-hmm.
You don't feel like it, but have those ones that are still on the line at the envelope. Would you say that's still not normally, or would that fall in normally?
You mean you've only had a few on the line of the dashed line?
Like I'm completely outside of
Yeah. In that case, again, the examiner is just looking for you to demonstrate your understanding that things inside that line are normally distributed and things out aren't. So I would say we clearly have some points on the red dashed envelope. It looks very close to being normally distributed. If it's anything like that that's a grey area, it's not more about whether you argue one way or the other. It's about whether you understand what you're talking about. So as long as you understand that key premise that inside the line is good and outside the line is bad, you can probably argue whichever way you want. If it were on the red dashed line, I would say that's still okay. I'd probably say that's fine. Overall, it looks normally distributed. It's sort of borderline. The weird thing about R-Commander as well is that you could run two normal probability plots and you may not get the same answer both times. It simulates that confidence envelope. And I think the processing power that it devotes to doing that will differ on different computers. And I've even done it on my own computer on different days and gotten a slightly different thing. So if things are very close, don't worry about it. It could be the case you run it again, they're all inside it. It could get worse as well. But they're that close that they're kind of within a plus or minus margin of error. In this case, this looks very obviously like there's something sus going on. There are too far outside of the line to be normally distributed. Yeah. But that's a general rule for all the questions. If you're not sure which way the answer goes, demonstrate your understanding. Demonstrate that you understand the basic concepts. Even if you don't get full marks, you should get something for showing that you clearly know something about statistics is what's going on there. Okay. So this is the first question where we've got some R-command output to deal with. It says it is desired to estimate the average protein content of protein bars produced by Muscleman Foods, and they take a sample of 20 bars. And output, we need to state a 90% confidence interval for the mean protein content of the bars and interpret the interval in the relation to the question. So in the output, you just need to dial in on this one here. Okay? It already says 90% confidence interval. If it didn't say that, you wouldn't even have enough information to work out a 95 or a 99%. So whatever percentage they gave you, that's going to be the percentage that's in the output, a 90% confidence interval. So all we need to say is quote those numbers. State the 90% confidence interval for the mean protein content. So what does it mean in the context of the question? With 90% confidence, something along these lines. With 90% confidence, we state that the true mean, or the population mean, the mean protein content, so I'm going to be specific to the context of the question, the mean protein content of what is it, muscle man foods? Yep. Mean protein content in muscle man foods protein bars is between, and that's where we quote the values that they gave us, is between, it was 28.180. I'm going to say grams. They didn't say it in the question, to be fair. And 33.581. 581 grams. Okay. So that would be how you'd answer that question from start to finish. What does a 90% confidence interval mean? I'm not going to go into the whole song and dance about if it's a 90% confidence interval, that means that 90% of all the sample means I take from the population should contain the real true value when 90 times out of 100, blah, blah, blah. You're simply stating that you clearly understand that a confidence interval gives you a range for the true mean value. Okay? I want to estimate the mean amount of protein in this particular brand's protein bars. I think it's somewhere between about 28 and 33 grams. Okay? With this level of confidence, 90% confidence. Okay? Obviously, if I could do better, I would, if I had a 95% confidence or a 99, but there's a trade-off to that. And that leads into the next question, because the next question asks us, which of the following is the upper limit of a 95% interval for the exact same data? So you should know that you can't calculate this by hand, and R Commander only gave you the 90% interval. So how do you know what the 95% interval should be? Well, you can work it out logically, what it should be. Based on the fact that the 90% interval goes from 28 to 33, I'll draw a thing here. This is not part of the answer to the question. This is just for you. 28.8 or 180 and 33.581. Okay, that was a 90% confidence interval. A 95% interval should be bigger, should be wider. Okay, if I want to be more confident, I need to either change the sample size or I need to increase the width of the confidence interval. Okay, so we are working with the same data, the same output. We don't have the option of changing the sample size to get a better confidence interval for the same width, right? We can do that. We looked at how to do that with calculating the required sample size for a particular confidence interval. We don't have that option. They didn't ask us about that. They said all else being equal, we're not going to change the sample, not going to change the sample size. If I went from 90 to 95%, the only way to do that to become more confident is to encompass a larger range of values. Okay? So it's a trade-off. Yeah, I'm more confident, but I'm less precise in my statement of where I think the mean is. So given that we now realize, or we recognize, that a 95% interval should have lower and upper bounds, respectively, smaller and larger than the 90% ones. We need to look at the upper bound of the 90% interval, 33.58, and ask ourselves which of these four numbers they've given us is larger than that. And only one of them fits the bill. Logically, that one must be the answer, 34.15. 4.15, okay? So I have drawn all of this just for the illustration. This is not something you need to draw to answer the question. By all means, as I've said before, keep some scrap paper nearby, draw little pictures every now and again to help yourself visualize what's happening. The actual way that you would answer that question is simply select the value, 34.15, and you can get rid of all this other junk that I just drew there. Okay? So those are the two answers. I should keep it all in blue to be consistent. Those are the two answers for those two questions. Confidence interval and 90% and 95%. Okay? So it just requires you to understand what a confidence interval is and what happens if you increase the size of your confidence. Okay? Any questions about that one? Everyone's happy? All right. Okay. So the next one, a government regulator of pharmaceuticals believes that the active ingredient in a tablet is more than the stated dose of 12 milligrams. So they've got a hypothesis. They think that something's wrong with these particular tablets on the market. To test whether or not they are correct, they take a sample of 12 and test for the amount of active ingredient in each of those 12 tablets. So we've been asked, given this situation, to write down the null and alternative hypothesis, find the degrees of freedom, and work out a conclusion based on the doing the case study stuff. I said I was being a bit vague on how you should write it out because I do it properly this week, so I will do it properly this week. Also, if you're interested in that case study one, if you want some extra revision, I did put up the complete lecture slides to that lecture, just in that folder with all the other lecture drawings. So it's got all those slides with the actual null and alternate hypothesis and conclusion and all that for every single question that we did last week. So for this one, again, I need to ask myself what is happening. This is a single sample t-test. I've got a single sample, just one sample of 12 numbers. From those 12 numbers, I'm going to calculate a sample mean and try and infer from that sample value if the true value across all of the tablets is bigger than 12 milligrams or not. So it's a single sample t-test. So this is how I would write it out for part one. Part one. Again, clarify in your own head what you're doing. It is a single sample t-test. What is my parameter of interest? Well, it's a mean, obviously. I'm going to say that the mean in this case is the mean active ingredient in these tablets. They didn't give us any more. I'd like to be more specific, if they gave us a brand name or something like that, but they didn't give us one. So we can only be as specific as the question was. And I'll put that that's in units of milligrams. My null hypothesis, stated in terms of that mean parameter, is that the mean is equal to 12 milligrams. The alternative, this is where I have to read the question carefully. They suspect, the government regulator suspects that the active ingredient is more than the stated dose. So I'm looking for evidence that the mean is larger than 12. Okay? And that's it from start to finish for part one. Okay, you don't even need the single sample t-test at the top. That's really, again, just to clarify in your own head. But you should have a definition of your parameter. Again, that helps you clarify in your own head, if nothing else, what you're doing. What am I talking about? What's the parameters? And therefore, what kind of test should I be doing? That's the mean. That's what I'm testing. Okay? All happy with that? So the next one says, what are the degrees of freedom of the test statistic in this sample? So you need to ask yourself, what are the degrees of freedom for a single sample t-test? And this is probably a good point to have a little segue, something I meant to mention at the start and then forgot about it. When you come into the final exam, I would come in with a table that looks something like this. A table that you create yourself. It's a summary table of all the test statistics we've looked at in every possible different situation that we've done. I can see people taking photos of it. There's not a lot there. I deliberately didn't fill out much. I filled out one for single sample t-tests and started to fill out the one for independent samples just to give you an idea of how I would construct it. Because really, most of your learning will happen when you do this yourself. You have to sit down and, like I said, clarify in your own head what it is you are doing. So you go through all the lectures on hypothesis tests. What was the situation we looked at? Well, we had a single mean. We had two means. If we had two means, we had a bunch of situations we had to consider. We had a situation where we had two means from populations where we knew what the population standard deviation was, and we said it was the same for both populations. Then we had another one where we said we don't know what the population standard deviation was, but we're still going to assume that they're the same for both populations. Then we had the last one, where we said we didn't know what the population standard deviation was, and we couldn't assume that they're the same, and we had a different test statistic for each one of those three cases. Each case had a different test statistic, each case had a different number of degrees of freedom. So I've broken it up into that way. So go back through the lecture notes and make some kind of table like this yourself. You don't have to do it all in one go. You're going to start out with something that's very messy, that you'll then want to go back and clean up and make it nice and crisp and clean on a couple of sheets of paper to take into the exam. And that is where you will be able to work out what it is exactly that you're doing in every single situation, hopefully. You think, what's the scenario? Single sample, independent samples. Then we had paired t-tests. Then we had analysis of variance, blocked analysis of variance, chi-squared goodness of fit, chi-squared test of independence, test of correlation, test for slope. So there's a lot there. As I said, I didn't fill out very much, all right? Because it's up to you to do the rest of it. That is what I would, it's not just a good thing to have for the exam, but I think it's a good way to revise the whole topic. You do that yourself and you start to get to grips with what's actually happening. And more to the point, you see the similarities more than the differences across all of these different tests that we do. There's always this basic idea of how far away am I from what I expected to get in terms of some measure of spread. For a single sample, the measure of spread was the standard error where we calculate it as sigma over the square root of n, or s over the square root of n, if we don't know what sigma is. Okay? So do something like this. Ask yourself, what is the situation? Therefore, what's the test statistic? And therefore, what are the degrees of freedom in each case? Okay? Something like that, I think, would be a great thing to have. Someone asked me last week if they could send me their table that they'd been making to check if it's correct, and that's fine. As I said, I'm not going to do it for you. That defeats the purpose. This is where your study happens. This is where your learning happens, doing this yourself. But I'll check. I'll see if you made a mistake anywhere or something like that. You can send me a photo of it, and that's fine. Okay. So what's our situation for the test that we were doing? We were looking at tablets, single sample. We had 12 values in one sample. We wanted to test if that gave us a difference from what we expected. Our sample mean would be whatever. Mu naught would be 12. That's what we're expecting to see. And our standard error would depend on the sample standard deviation, right? They didn't give us any of that information, so we don't need that one as much as we need this one. How is that test statistic distributed? It is a t-distribution with n minus 1 degrees of freedom. So this is the most basic one we have. This is the one we started with. N minus 1 degrees of freedom. Very easy to remember. Gets a bit harder when you start talking about independent samples. You've got n1 plus n2 minus 2 for one of those cases. And then when you look at the situation for unknown sigma and you can't assume they're the same, it was a very complicated formula. Do not bother writing that down in this thing. You're never going to be expected to use it. But that's the idea. Build up some kind of table like that yourself. And I think it will be extremely helpful. So that's what I wanted to do. Check my table that I've got in the final exam with me. How many degrees of freedom do I have for a single sample t-test? I have n minus 1 degrees of freedom. And the information I need is n, the sample size. No, 12. They are 12 samples. So I have 11 degrees of freedom. Okay? Easy as that. Easy mark to get as long as you know what to look for. So the next question says a p-value of 0.013 is obtained. Is this significant at the 1% level? So my significance level, probably convert it to a proportion before you do it, because again, it's a very common mistake for people to make, where they forget that one of them, the p-value is a proportion, and the significance level is a percentage. And they compare the two, and they're probably going to get the wrong answer. If you convert one to the other, to convert a proportion to a percentage, you multiply by 100, which tells me that a p-value of 0.0, what was it, 0.013, whoops, 0.013, multiply that by 100, that is equivalent to 1.3%, okay? Or you could take your significance level of 1% and divide that by 100, and that is equivalent to 0.01. Either way, you just need to compare the two numbers, but before you do that, you have to make sure that they're the same thing. Don't compare a percentage to a proportion, you're going to get the wrong answer, probably. So I've converted the significance level to 0.01. I need to say which one is bigger. And again, this is a point in exams where people are stressed and not thinking properly. And I find especially when numbers are less than 1, people struggle to figure out which one's bigger or not. The p-value is bigger than the significance level in this case. You could think of that as 13 thousandths, whereas the other one is only 10 thousandths. So p is bigger than alpha, and we do not reject the null hypothesis in this case. We don't reject H0. Then that's my decision. I need a conclusion specific to the context of the question. We do not have enough evidence. We do not have enough evidence to suggest that these tablets have more than 12 milligrams of active ingredient on average of the active ingredient on average. Okay, so very specific to the context of the question. Always break it down into those two sections. Your decision, which is simply reject or don't reject the null hypothesis. Your conclusion then indicates to the examiner whether you actually understand what it is that you just did. And again, very common mistake for people to completely reverse the two. They'll say, I don't reject the null hypothesis, therefore I have evidence that the tablets have more than 12 milligrams on average, right? Those are two completely opposite things. They can't both be correct. I didn't reject the null, therefore I have no evidence to support the alternative, as opposed to, if I do reject the null, I do have evidence to support the alternative. And we've done that many times now. Again, last week was one of the weeks where we did it. I think worksheet 5 was the prac worksheet that had a lot of null, alternate hypotheses like that. So make sure you understand those basics. That's really the crux of statistics, the p-value. What's the probability of getting this thing if the null hypothesis were true? That's how you make your conclusion in statistics. Okay. So there's parts 1, 2, and 3. Again, not that difficult. In fact, no mathematics aside from going 12 minus 1 is 11, and the p-value is bigger than the other number. Like, there's no maths there. It really is whether or not you understand what's happening. Okay? So easy marks to get as long as you know what's going on. Any questions about that? Okay. So the next one. A motor engineer wishes to test whether the efficiency of engines is improved by a fuel additive. So they take 15 different engines and then measure the efficiency with and without the additive. And they say normality can be assumed because that was one of the assumptions we had when doing a paired t-test. So I've given away already what the answer is. They want us to write down the null and alternative hypothesis for this particular scenario, but they've given us 2 different types of R-commander output. They gave us one for a paired t-test and one for a 2-sample t-test. Okay? R-commander will do both of them based on the same data that you gave it. It's up to you to work out which one you should do. And we should be doing the paired test because we've measured each thing more than once. We've taken each engine, and again, you can draw a picture or draw a table to think about it in your own head. We had engine 1. We measured the efficiency with the additive, and again, without the additive. And you build up this table. You've measured every engine up to, we had 15 engines. Engine 15, with and without an additive. So every engine has 2 values attached to it, one with the additive, one without. We should pair those numbers up. We don't want to treat both of those columns as independent sets of numbers because there's going to be variation between the engines. They didn't tell us that they're all, the same Mercedes-Benz engine or something, the exact same model. Different engines from different cars, presumably. There's variation between the engines that has nothing at all to do with testing whether or not the additive is making a difference, right? Obviously, you put it into a V8 engine in some, beefy Holden, or you put it into some 4-cylinder Holden Barina. There's going to be differences in performance, okay? There's going to be differences in performance that's got nothing at all to do with whether or not the additive is making a difference. So we do a paired test. The observations are not independent. We've measured each thing twice. We pair them up. When you do a paired test, You don't have to do this by hand, but what you're doing is creating a new column for the difference between those two values. Okay? So you'd maybe have a value like 10 here and a value 9 here, and you get a difference of 1, 12 and 13, -1, and so on and so on and so on throughout the whole thing. At the end, you just restrict yourself to looking at that column and you say, what was the average difference? That's a paired t-test. And that's critical that you understand that idea, because that will determine how we write our null and alternate hypothesis. It's not going to be the same as we would write them for an independent samples test. So that's the idea. I want to find the average difference, mu d. Let me move that over, get it out of the way. Okay. So write down the null and alternative. Part 1. Again, I clarify in my own head what I'm doing. I'm doing a paired t-test. Paired t-test. What is my parameter? My parameter is the mean difference. The mean difference. And this is where we need to be careful, because that difference will be different depending on how we define it. Do we go with additive minus without the additive, or do we go without additive minus with? Doesn't make any difference as long as you're consistent. We don't have a choice though. They've given us the output from our commander. We just need to see what did our commander do, and it tells us it went without minus with. Okay? In that order from left to right, that's the way it has done it. You can read that as without minus with additive. So that's the way I define my difference in my null hypothesis as well. So the mean difference, where I've measured the difference as without additive minus with additive, mean difference. The null hypothesis states that there is no difference, right? I'm looking for evidence that there is a difference. The null hypothesis will assume that there is none. The alternative, specifically with that definition, I need to be careful. If I'm calculating the differences without minus with, and let's say that higher efficiency means a higher number, then I'd expect the mean difference to be negative. Because if you don't have the additive, you subtract that from the number with the additive. The without additive number is smaller than the with additive number. You should get a negative number on average. So that's what I'm looking for. I'm looking for mu d is less than 0. The average difference is less than 0. If you change the difference to being with additive minus without, you'd have to swap that sign over. You'd be looking for a positive difference. So it depends how you define it. You just have to be careful. Paired t-test, we've already decided that the paired t-test is the most appropriate one, so you just need to pick out the p-value from that. That's all it is, 0.001231. .001231. Okay. Oh, sorry, I have to be careful. I have to be very, very careful. Yeah, exactly. Well spotted. I was just thinking how easy that was. I'm like, that's too easy. Normally the questions aren't that easy, at this stage of the exam anyway. As was just very astutely noted, look at the alternative hypothesis that they calculated that p-value for. That was for an alternative hypothesis where you were doing a two-sided test. Mu d is not equal to 0 is what it's telling me. That is the two-sided p-value. I need to halve that number to get the one-sided. So this is, again, this is where maybe you would draw a picture yourself. This is not part of the question. But to clarify in your own head, I have a t-distribution. My test statistic, according to them, is negative 4.03. It's down here somewhere, negative 4.03. Now, our commander has done a two-sided test for me, which means it went at 4.03 and negative 4.03 and calculated the total sum of both of those areas. I just want what's down here. So I need half of 0.01231. So I just need to divide that number by 2, and that gives me 0.123615. Okay. Again, very tricky. Have to be very careful. My alternative hypothesis didn't match the one that our commander has, so my p-value doesn't match it. And again, that was all the stuff we did in worksheet 5, where you were given possibly a number, probability. They didn't say it was the p-value. It may be the p-value, but it depends on the alternative. It may be that number, it may be 1 minus that number, it may be twice that number, it may be 1 minus that number and then double that or something like that. It depends on the alternative hypothesis that you've got. So mine was less than, Archimander's was not equal to. I need to think about that, draw a little picture and say, that's what Archimander gave me in red. I only want that area that I've circled down there in blue. Okay, so I need half that total. Any questions about that one? Okay. So last again, using a 5% level of significance, what is your conclusion? Write a sentence in the context of the question. So again, this is very similar to what we did before. So now I have a 5% level of significance. It wouldn't have actually mattered. A 1%, it's still significant. So 5% is 0.05 as a proportion. My p-value, which we have above, 0.000615. Again, it's very formulaic, the answers to these questions. We say since this case, the p-value is less than the significance level, we do reject the null hypothesis. What does that mean in the context of the question? We do have evidence. We do have evidence to suggest that something about the fuel additive is working, to suggest that the engines run more efficiently with the additive. Okay. Same thing again. First part was just the decision. Is this number bigger or smaller than the significance level? Then we have a conclusion in the context of the question. Okay. Everyone happy with that? Cool. All right. How are we doing for time? Not too bad. I won't have a break because I want to make sure that I get through it, but I get through it without rushing too much. So if you need to duck out, that's fine, but I'm going to keep going. Question 4 is an ANOVA question. It says a study was conducted, again, about protein content in 4 different brands of protein bar. From each brand, they took a sample of 5 bars, and then this is the data that they got from Archimander and its ANOVA table, and they want us to answer a bunch of questions about this. So the first one says, describe how the F statistic is calculated. That's quite a strange sounding question. What they're looking for is that you understand how the F statistic 1.63 emerges out of this table of numbers. And I would simply say something along the lines of, it is calculated as the ratio of the mean squares of the treatment, or in this case brand, and mean squares of the error. Okay, specifically, in this case, it was 39.95 divided by 24.49. It's calculated as the ratio of those two numbers. That should give you 1.63, approximately. So something along those lines. Doesn't have to be word for word the way I've written it. Something that indicates that you know that the F statistic is this number divided by that number. Okay. The next one is asking us to find the missing values in the table. So there's some missing degrees of freedom values in there with question marks over them. We need to find what those are. So I'll start with the brand. The brand is the treatments or the different populations. I have, what did I have? 5 brands? 4 brands? 4 brands. 4 brands. So these are my treatments, is what we've been calling them for a while now. Or populations. When we first started ANOVA, we called them populations. Same thing. And this is the one that will give me the degrees of freedom for between the populations, between the brands. Okay. So this one is the simplest one to calculate. The degrees of freedom for between the brands, degrees of freedom for the brand is equal to the number of brands minus 1. So we had 4 brands, we have 3 degrees of freedom. So I didn't put it on the table because in the exam, obviously, you'll be writing your answers on the given workbooks. So don't write it into the question paper because the question paper isn't marked. You need to write it into your workbooks. So there's the degrees of freedom for the brand, k minus 1. We need the degrees of freedom now for the error, which is n minus k. Capital N is the total number of observations that we had across all the brands. We had 4 brands. From each of those, we took 5 protein bars. So we have 4 times 5. We have 20 total numbers of observations across the whole thing. So N, capital N is 20. The number of brands is 4. We have 16 degrees of freedom. So 3 and 16 are those 2 numbers. Not terribly difficult questions. Again, the maths is just minus this number from that number. This is where having that table of test statistics, degrees of freedom, all that kind of stuff would help you. You don't want to be wasting time in the exam trying to relearn analysis of variance to work out what these things are. Have it all laid out in a table, degrees of freedom for the brand, for the error, all that kind of stuff. Okay? Any questions about that one? Next one. What are the degrees of freedom of the F statistic? So this is a simple question as long as you remember the correct order in which they are written. So the degrees of freedom, if you remember, an F statistic always has 2 numbers for its degrees of freedom. Unlike a T distribution, it only has a single number that determines its overall shape. An F statistic has 2 degrees of freedom, and it's those 2 numbers that we just worked out. The degrees of freedom of the error and the degrees of freedom of the brand. And typically, we write them in the order n minus k, k minus 1. The order won't matter as much. If you label them correctly, n minus k, k minus 1, then the examiner can see what you've done, that you got 16 and 3. Was that the convention or was it the other way around? As I said, it doesn't matter as long as you label them. You know, this one's n minus k, that one's k minus 1. 16 and 3, those are the 2 degrees of freedom for the F statistic. Next one. Using a 5% level of significance, it is claimed that there is no difference in protein content based on these results. So you could assume the reason they made that claim is because the p-value is bigger than 5%. It's a 22% p-value. But there's a problem with what they've said. They said that according to that p-value, there must be no difference in protein content based on those results. The main thing that they've done wrong, this is the one time where I will ask you a question. Does anyone know what the mistake is in the wording of that sentence? They've done something you should never do. That is not a possible outcome of a hypothesis test, which is accepting the null hypothesis. You can never accept the null hypothesis. This is incorrect. I'll zoom in a little bit so you can see it better. This is incorrect as it amounts to accepting H0, the null hypothesis. Okay? At the end of a test, failing to prove that there's a difference isn't the same as proving that there is no difference. Okay? That's the common thing we've said many times. Failing to disprove something isn't the same as proving the other one. Just because I didn't disprove the null hypothesis doesn't mean it's true. So they failed to disprove the null hypothesis and they said, hey, look at that. That must mean that the protein bars all have the same mean protein content. Because we were looking for evidence that they didn't have the same mean protein content. We didn't find that evidence. Therefore, they must have the same mean protein content. No, that's not true. We never accept the null hypothesis as a possible outcome. Or you could say at the outcome of that test is that you have no evidence to support that the protein content is different. That's it. It's inconclusive. It doesn't mean they're the same. I just have no evidence to support that they are different. That is the correct conclusion that you should make based on that p-value. Okay. All happy with that? Yep. So the next one is a chi-squared test question. They give us a table that amounts to 210 total sightings. That's useful to know because we may need that later. 3 species of bird counted in 3 different habitats, 210 total sightings. So the idea is that we have 2 qualitative variables here. The first variable is habitat, which could come in 3 flavors, 1, 2, or 3, whatever they are, it doesn't matter, 3 different habitats. The second variable is species, owl, crow, or eagle. 2 qualitative variables. Suggest a research question in the context of the question that this data may have been collected for. You can answer a few things about this data, all of them chi-squared test kind of questions. I could ask if a particular species is evenly distributed among the 3 habitats, like if I restrict my view to just owls or crows or eagles. I could ask, does it appear that they have no preference in where they live? Or I could ask whether there is a relationship between species and habitat. I could say, does being a crow increase the likelihood of me finding you in habitat 3, or does being an eagle increase the likelihood of me finding you in habitat 1? We can't be that specific at the end of the test, but we can simply say, is there a dependence between species and habitat? Does it affect where you're going to find the species? Okay, depending on the location. So my actual answer to the question would be something like this. What subpart are we doing? We are doing B1. So B1, research question could be is a particular bird species, let's say, evenly distributed, or evenly distributed across these habitats. So that would be a chi-squared goodness of fit type of question. Single qualitative variable, 1 species of bird. Is it evenly distributed? You don't even have to ask if it's evenly distributed. You could test for whether it's distributed, 50, 40, 10 or something like that. But just is the bird species, 1 species spread across the habitats in a particular way. The other one would be like a chi-squared test of independence. Does bird species, or does habitat, or is there a dependence relationship between species and habitat? Something along those lines. Are they independent, species and habitat? That would be another question that I could ask with this particular set of data. Okay. And either of those would be fine. They simply said suggest a research question. So you've suggested a research question. You could do a goodness of fit style test. You could do an independence style test. Either one is fine. Either one is doable with that set of data, basically. Okay. So the next one says, if a researcher is testing whether species of bird and habitat cited are independent, you'll notice they actually sort of gave away the answer to the previous question. You could use that. That was the research question I just wrote down, the dependence one. Are they related to each other? So they gave it away in the second part. You could use that to answer the first part. If they are testing for that, what is the degrees of freedom of the chi-squared test statistic used? So to work out the degrees of freedom for a test of independence, it is the rows minus 1 times the columns minus 1. So I ask myself, how many rows do I have in my table? How many columns do I have in my table? Multiply those two together. Sorry, how many do I have minus 1 in each case? And that gives me my degrees of freedom. And again, that would feature in your summary table of all your test statistics once you get there. I know I made it sound like a lot. There are a lot of tests we've covered. Tests for means include single samples, independent, paired, and ANOVA. Tests for proportions, chi-squared goodness of fit, chi-squared test of independence, and then tests for linear correlation, which could be testing for the correlation coefficient being different from 0, or for the slope being different from 0. So there's a few tests, but you might be surprised how quickly you knock them all out into a table once you go back through all of the lectures. And making it that much smaller and denser and more concise for yourself will definitely help. So in our case, we should have 4 degrees of freedom. B, degrees of freedom for a chi-squared goodness of fit test. It's the number of rows minus 1 times the number of columns minus 1. 3 minus 1 times 3 minus 1 is 2 times 2, which is 4. Okay. Happy with that? Next one. For a chi-squared test in this situation, so doing a test of independence, a p-value of 0.039 is obtained at a 5% level of significance. What is your conclusion? So again, this is one of those cookie cutter questions. I just say, here's my p-value. My significance level was 5%. My p-value, I always like to write them down side by side just to make sure I don't make an easy mistake. P-value 0.039. Again, we simply say, since one is bigger or smaller, in this case the p-value is smaller than the significance level. We do reject the null hypothesis. We do reject H0. That's my decision. What does that mean in the context of the question? Now I need to write my conclusion. And I would say that we do have evidence. We do have evidence to suggest that species and habitat are not independent. Habitat are not independent. Again, specific to the context of the question. Maybe I'll put in bird species there. Be a bit extra specific to make sure that we understand what exactly it is that we're talking about. What has our test actually shown that these things are independent? Okay? So that's from start to finish the first 3 parts of B. Again, not a lot of actual working, you'll notice. Not a lot of maths going on. Still just some very basic calculations that depend on you knowing some basic facts about these types of tests. For part 4, they say, suppose we only consider habitat 2, and researchers predict the 3 bird species are sighted according to 30% owls, 50% crows, and 20% eagles. So now, we're just dialing in on this row in the table here. We're going to ignore everything else. We want to find the expected counts for this particular test. So we expect the numbers to be in the ratio 30%, 50%, 20% owls, crows, eagles. I need to calculate what do I expect to see in that case. So to do this, let me move this down. I'll need that later. Made that earlier. Get rid of that. So for part 4, how do I calculate my expected counts? First, I want the total number of birds in that particular habitat, in habitat 2, which was 25 plus 45 plus 10, which comes out to be 80. So there were 80 birds in total. What are my expected counts? Expected number of owls. According to what they said in the question, they expect that out of these 3 species of birds, if you were to count them in habitat 2, 30% of them should be owls. So I'm looking for 30% of 80. Happy with that? Again, being careful when you convert from percentage to proportion. If you multiply 30 by 80, you're going to get a ridiculously large number of owls. Make sure that you do that conversion. 30% of 80 is 24. You can type that into your calculator to check that. That's the expected number of owls. How many, what's next? Crows. How many crows do I suspect or expect to get? They expected 50%. 50% of the 80 counted should be 40. And the expected number of eagles, they said that it should be 20%. So 0.2 times 80 gives me 16. So it's that easy. calculating the expected values. You'll notice, obviously, that the proportions they gave us add up to be 100%. That has to be the way. 50 plus 20 plus 30 is 100. And so the expected number of owls, crows, and eagles should add up to be the same total as what we had. The point is you're calculating it based on the sample total. They gave you the proportions. Those proportions should apply to a sample or a population of size 1,000 or 10,000 or 10 million. Okay, the point is we have a sample of 80. Out of those 80, if the proportions are correct, how many do I expect to see in each case? I expect to see 30% of that 80 as owls, 50% of that 80 as crows, and 20% of that 80 as eagles. Okay? And that is how you would answer that question from start to finish. Again, that's how you'd actually answer it in the paper. Happy with that? It's critical that you get that right, although if you didn't, you're not going to get double marked down. But the next question says, calculate the chi-squared test statistic if the researcher's predictions above, for what we just worked out, are correct. So this is a goodness of fit test because it's a single qualitative variable, location, the habitat, split into 3 categories. I'm just going to rewrite those values over here because when I do a chi-squared goodness of fit test, I find it's very helpful to put the observed and expected numbers right next to each other as you calculate your test statistic, okay? That's going to help us a lot. So we need to work out the chi-squared test statistic. Now this could be for a goodness of fit or for a test of independence. It's up to you to work out which one you've got. I have a single qualitative variable, as I just said, single qualitative variable. That implies that this is a chi-squared goodness of fit test. And I need to calculate the chi-squared test statistic. And this is the one that I've said throughout the semester. Be aware, you're not expected to do many calculations by hand for a lot of the formulas, but you are expected to do a couple, and this is one of them. So the chi-squared formula says that we should add up from 1 to however many categories we have in our qualitative variable. We have 3, owls, crows, and eagles. From 1 to 3, I want to take the observed count minus the expected count in every category, square it, and then divide it by the expected count. And that's why I kept that table there, so that I could keep an eye on the observed and expected and making sure that I'm matching them up correctly as I should. So I'll do this one slowly for you. So in the first category, I could label these however I want. I'll call that I equals 1 for owls, I equals 2 for crows, I equals 3 for eagles. It doesn't actually make a difference if you swap that order around, because I'm just going to add them all up in the end anyway, as long as you keep those pairs of numbers together. Keep the owl numbers together, keep the crow numbers together. So observed number of owls, 25. I actually saw 25 in the original sample. I expected 24. What is the square of that difference divided by what I expected? So that's the owls. I'll just label that to make it super obvious. That's the owls. The next one, what did I observe? I observed 45 crows in the original sample, but I expected, according to what they told me, I expected 40. What is that squared difference relative to what I expected? So that is my crows. The next one, I saw 10 eagles in my original sample. I expected 16. What is that squared difference in terms of what I expected? 16. And that is for the eagles. As long as you get that correct, the rest is just very, very carefully plugging it all into your calculator. And I would suggest doing it one term at a time. I never do because I'm too impatient. I try and type it all in one go into my calculator. But in a final exam, to avoid making a silly mistake, work out the first term for owls. That's going to be 1 squared over 24. Put that down as its own separate number. Work out the one for crows, put that down. Work out the one for eagles, put that down. And then go back and add them all together. Okay? So that's all just an exercise on your calculator. The final answer should come out to be approximately 2.92. And they didn't ask in the question, they didn't say quoted to any specific number of decimal places. So you can do whatever you feel like. Probably a couple of decimal places is usually the standard. That's the safe one. But you're not going to get marked down if you go 3 or 4 or 5. Doesn't matter. They didn't ask, so you don't have to give them a specific number. So there's our test statistic, 2.92. We would look at a chi-square distribution if they asked us, a chi-square distribution on 2 degrees of freedom, the number of columns minus 1 for a goodness of fit test. We would look at a chi-square distribution with 2 degrees of freedom and say, what's the probability of getting a chi-square test statistic bigger than about 2.9? And based on that, we would be able to say, does it look like these birds are distributed in a way that is different from what I expected? Intuitively, I'd say the answer to that is no. Maybe check that yourself on our commander at home. You look at those numbers, they don't look that different. They don't look that different, but I'm not sure. A test statistic of 2 or 3 on a chi-square distribution with only 2 degrees of freedom, I don't think that's going to be a significant p-value. I don't think you're going to get evidence that those birds are distributed in a way that is different from what we expected, 30%, 50%, 20%. Okay? They didn't ask us to do that though, so that is all you need for that question. The table, I'll leave it in black. You can include it or not. It's not necessary to answer the question, but I do like to write a table myself when I answer these questions, just to make sure that I'm matching up those observed and expecteds correctly when I calculate it. Okay? Any questions about that one? That's probably the most mathematical working you'd be expected to do for the final exam. Some kind of chi-square test question. Involves the most calculations. Okay, we are at the last question, which is good. Did pretty well for time. In a study to investigate the relationship between brain mass and body mass, they have given us the units of each. That's good, we need that. Of various animals, they took 23 different species and got some simple linear regression output from our commander. So the idea is they take like a field mouse, a whale, a human, a pig, 23 different species, and say what's the mass of their brain on average, what's the mass of their... I want to be very careful. Again, this is my slope direction, depending on whether the sign of the slope is positive or negative. So that's the general rule. I need to be specific to the context of the question. So I'd say for every unit increase of x, for every 1 kilogram increase in body mass, they told me in the question that body mass is measured in kilograms, so I know that's the units. For every 1 kilogram increase in body mass, we expect or predict, we predict a 1.009 gram, that was the units they told me for brain mass in the question, increase in brain mass. Okay, it's an increase because there's a positive sign sitting in front of the slope. If that were negative, then I'd say a 1.009 decrease in brain mass. So you have to be very careful because most of the examples we've had have been positive slopes. Won't necessarily be the case. It could be a negative slope. Again, it just requires on you knowing which number is the slope and then therefore what does that mean? If I were to try and picture it, I'd have an x, I'd have body mass predicting brain mass. There's some equation. What was the 129? There's some equation that relates them, some linear equation. It is the slope of this equation. For every 1 kilogram increase in body mass, there is a 1.009 gram increase in brain mass. That is what the slope is telling you. The rate of change of that line. Okay? Any questions about that one? So that's both those questions answered as you would answer them in the final. Using a 5% level of significance, is there evidence of a relationship between brain mass and body mass? So to work that out, we're looking for evidence of a linear correlation. And to find statistically significant evidence, you need a p-value. The p-value that we need for linear correlation is the one that corresponds to the slope. This one here. Whoops, need to dial in just on that one there. Okay? Because if you remember, there's 2 ways to test for a significant linear correlation. The first way is to do a test on the correlation coefficient itself. That's the number that tells you if there's a linear correlation. You test for whether or not the correlation coefficient is different from 0, and you get an answer. The other way to test it, which is completely equivalent, you'll get the exact same p-value, is to test for whether or not the slope is different from 0. Because if the slope equals 0, your line goes flat. It means that no matter what x is, y doesn't change at all. Y doesn't depend on x. It doesn't respond in changes to x. So if you do a test for whether or not the slope is significantly different from 0, you find evidence that there is a linear relationship between these two things. One is responding to the other. And we do have a very small p-value, 0.0075. So I would say, so that was for part B. So for part C now, again, it's that same old formula. I'll just write down my significance level and my p-value so I don't get lost. P-value 0.0075. Since p is less than alpha, we do reject the null hypothesis. Reject H0. What does that mean in the context of simple linear regression? We have evidence. We do have evidence. We do have evidence to suggest that there is a linear correlation, specifically linear. We don't worry about other types of correlation in this subject, but other types exist. There is a linear correlation between body mass and brain mass. They were the variables, weren't they? Yeah, body mass and brain mass. Okay. Happy with that? As I said, same as all the others. I always underline those two words, do, in the decision and the conclusion, because they're really the only two words that kind of change. If p was larger than alpha, I'd say I do not, or I don't have evidence, and therefore I don't reject the null hypothesis. P is less than alpha, you do have evidence, you do reject the null hypothesis. Okay? What percentage of variation is explained by the linear model? So this is a relatively recent concept for us. We've been covering this the last couple of weeks. To find the percentage of variation explained by the model, we want to dial in on one number in that output, and that is the multiple r-squared value. And you'll always find that down there. Don't look at the adjusted r-squared value, which isn't hugely different, but that is not the one that you want. You want the multiple r-squared value. And that's the value. That's the value as a proportion. What percentage of variation is explained by the model? I take that value and multiply it by 100. I'd say 29.4% of variation in the response variable, so brain mass in other words, of variation in brain mass is explained by the model. Okay. So that r-squared value, that multiple r-squared value, gives you a way to quantify how good a job your linear model is doing. Because more often than not, you can find linear relationships between things. Again, that doesn't imply cause and effect, that one is causing the other to happen. But that's separate from how good a job the line is doing at predicting values of your response variable. So it's saying that it does seem like there's something going on. Your body mass does help you predict in some sense how big your brain will be. But it's not a great prediction. Only about 30% of the variation in brain size across all species, or the species they sampled from, is accounted for by this linear model. So body mass goes some way to explaining your brain mass size, but it's not the end of the story. And that's what I'd probably suspect. It's a very oversimplified way to look at life, isn't it? You would not expect brain mass to be a perfect one-to-one correlation between your body mass, right? A silverback gorilla is a lot heavier than I am, but I'm reasonably confident I'd have a larger brain, right? Maybe not by much, okay? They're not that much smaller. But that's the idea. I mean, a whale, a blue whale, is a massive beast. Proportionally, though, how big is its brain relative to that body mass? It will definitely be bigger, but it doesn't necessarily increase. It's not perfectly predicted by your body weight. Okay, that's what this is saying. Only about 29.4% of variation in brain mass is explained by that model. The last one is one of the easiest ones. This one is just a little bit of calculation. What is the predicted brain mass for a pig with a body mass of 200 kilograms? So now we actually use our model. This is what the model is for, to make a prediction. So we say that brain mass, according to our model, the formula, the very first thing that we wrote down was 129.516 plus 1.009 multiplied by body mass, and they are telling us that that is 200 kilograms. So I plug in 200 kilograms. And if you put all that into your calculator, you should get 331.316. That's not quite the end of the story. They asked me to predict brain mass. All I've done is given you a number. So therefore, a 200 kilogram pig, we predict to have a brain mass. So we have a brain mass of approximately, because it's only a model that we know is only doing about 30% of what it could, brain mass of approximately 331.316 grams. They didn't ask me to round it to any particular decimal places, so I can just leave it at that. Okay? So we're done. Are there any questions about anything? So I won't be back at Hawkesbury. My home campus is Campbelltown. I'm not going to be back here probably for another year. But by all means, email me at any time from now until the final exam. You can email me, again, remembering during business hours. I'm not on call 24/7. I have had many students in the past email me at midnight the day before an exam. Good luck. And obviously, I'm not checking my emails at midnight. I don't know what you expect. And on weekends as well. You can email me with any questions. Also, I won't be back here face-to-face. If you can't come to Campbelltown, we can set up a video conference meeting. There's an app called Zoom that you all have free access to as university students. If you don't know how to use it or if you haven't used it before, email me. I can show you how to download it. It's very simple. We can set up a video conference that way. Or if you live close to Campbelltown or feel like the trek, if you're really desperate for a face-to-face, again, email me and we can set up a consultation time. So my standard consultation hours won't apply to the exam period. We'll just do it by appointment, basically. We'll find a time that suits you, and then we should be able to go from there. Okay?